Make is an interesting tool. You've probably run into it before if you've installed any packages. It's sort of the classic open source tool that that is widely used to automate building and workflows. It's sort of stereotyped though, and it's also sort of considered old-fashioned. Um, I'm going to go through a few uh, different topics here. And I'll say something about each of these. So I'll just dive right into some of the details. So, like I said, it's a classic tool. One thing about it is that it's very much oriented towards the tradition in the Unix environment of modular tools, which do a small transformation and act as part of a pipeline or a graph of dependencies. So, in sort of old-fashioned Unix, you might be using C code. The C compiler takes .c files and generates .o files. Then the linker combines .o files into an executable. And there are ways that this can be ramified. So for instance, if you're making a library, the .o's might be combined into a library file. But this is sort of the typical Unix approach to putting together tools. And it applies to lots of other things. So for instance, if you're writing a document with TeX, a document processing language, TeX goes through various phases, each of which involves a tool that transforms one input into another. One of the central things that Make is good about is that it emphasizes the laziness aspect. So if you've got a big project that involves a lot of C source files or source files in general, and you modify one, typing make will only do the minimal set of transformations you need to get your output from the files derived from the file that you changed. In other words, when you make a change, make propagates updates, minimal updates, so it won't recompile anything you don't need to recompile. I think it's also important to point out that a tool like Make, a make file, serves an important aspect of reproducibility of doing science, because it's a standard, a very well understood standard for how a project is built. And in some ways, I think this suggests that Make should be used for outside of the typical examples. So, even if you don't have C code and you're generating an executable, there's no reason you shouldn't consider using Make for other purposes. Like I said, the stereotypical thing is C compilation units, a program that's broken into multiple .c files, or C++ or Fortran or whatever. Each of them then generates an output file, and then output files are transformed further into other stages. It's interesting to consider that this is sort of, this phrase separation of concerns is a common sort of software architecture concept. And the idea is just that you want to establish boundaries between tools so that the tool can be isolated from other tools and used modularly, sort of as a building block for bigger projects. This formatting of text in tables is sort of from the example of Unix tools for text formatting, which are sort of dated. If you run man on a Unix system, you'll be running a system called graph. And graph is very much in the standard format, the standard scheme for Unix modularity. So it has separate executables for formatting text versus tables. It has separate executables for dealing with things like compression. But in general, there are lots of pipeline stages. Well, there are lots of kinds of transformation that you might consider automating using Make. So, well, this is maybe a rabbit hole. One interesting note is that the C compiler on Unix has actually sort of broken this idea, because when you run something like cc hello.c-o hello, the C compiler is acting to automate some steps. So a strictly sort of hard modularity approach, the C compiler would actually not automate these for you. Because the C compiler is running a preprocessor, then it's running a code generator, and in this case, it's also running the linker to generate the .o file. Those could all be done. My point is, those could all be done with make. So here is sort of the canonical, simplest possible example. I did it in C, but none of this is specific to C. It could be Fortran or anything else that requires some transformation. And that even includes things like TypeScript. Scripting languages like Python generally don't introduce these extra stages, but they might benefit from dependency analysis as well. Anyway, so here is the simplest possible C program. Very simple. All it does is say hello world. If we type make hello with nothing else, make is smart enough to know that we derive the hello program from the hello.c input script. And again, if we type it twice, the second time make will say that hello is up to date, because it finds a file named hello, which it knows is derived from hello.c, and will automatically tell you this. Now, that I want to emphasize that's actually sort of the crux of how make works. So you give it a goal or target, and it figures out, it infers based on what it knows about the structure of your program. It infers what it needs to do to get there. So in this case, make has built-in knowledge of how you might derive an executable named hello from a source file named hello.c. So I guess the way I would describe it is that make allows you to factor out or abstract the steps that are taken to build things. And some of this, syntax like this is always a little bit like line noise because it's pretty deeply encoded. So this line is probably pretty obvious to you. I'm just creating a variable named uppercase cc, and I'm setting it to cc the executable. This could be something like ccomp, and this could be gcc instead, or some other compiler. This syntax here is the beginning of what we call a rule. And the structure of make consists of a combination of variables like this line and rules like this line. So the rule begins with a dependency declaration, and I'll explain this syntax in a minute, and then a sort of a body or payload. And these, in my subtitle, I called it declarative. It's declarative in a way that might be surprising to someone who's used to thinking of declarative as meaning, oh, well, I give it a YAML file, because this is not YAML, obviously. And the syntax is peculiar to make entirely. So for instance, the body of the rule has to begin with a tab character, which is, very odd by modern standards. But what this really means is that if you've got a .c and you want a .o, then run this. And this sort of looks like line noise as well, but if we decode it a little bit, it's maybe a little bit more understandable. So in this case, I'm referring to the variable, which I'll correct. So I set GCC to the variable, and I'm giving GCC the -c parameter, which means just compile an object file. And this bit of line noise is actually referring to the, let's say, depended on part of the rule. So it's referring to the .c code. So whatever .c file triggers this pattern will be substituted in here by make. And then -o is another parameter to the C compiler. And then this is another variable that gets substituted for basically the generated part. So this will wind up running gcc-c hello.c-o hello.o. The only other part of this is that I'm saying the program hello depends on hello.c. A lot of what make does is kind of silly in a small example like this. But in this case, I'm just saying, you know, I could call this hello, I could call this my program. Oops. I could call it something other than hello.c. And in that case, make is being instructed that to generate my program, which is the first goal listed here, my program depends on hello.c. So the makefile structure in general is variables and rules. They're interspersed as you will. It does matter which comes before which. So in that sense, it's not, you know, 100% declarative. And make basically reads the make file, fully processes it, and then interprets it. And by fully processed, what I mean is there's a certain amount of processing that goes along with the variables. And the rules basically build a dependency graph within make. So, you know, these rules are saying to get this target, the left side of the colon statement, requires these prerequisites and this recipe to transform the prerequisites into the target. That's the basic structure. The targets can be multiple targets, the prerequisites can be multiple prerequisites. The recipes are basically just after variable substitution given to the shell. And incidentally, you can choose alternative shells if you wish. The variables, I guess this is sort of oversimplifying, but there are two basic types of variables. One I'm going to call deferred and the other called immediate. When you say something like a variable name equals something on the right side, make just takes the right side and copies that into as a string. It doesn't interpret it at the time. Whereas with the colon equals form, the right-hand side is interpreted at the time of assignment, and the results are copied into the variable of name 2. And that's really important because I underplayed it a little bit here, but the right-hand side can actually be complicated. So you can run commands, for instance, that generate output to go into this, into a variable. I think I've got an example that shows that later on. So defining variables, this format is a bit more like shell, where evaluation of variables is delayed until use, whereas this is a bit more like a programming language in the sense that you're doing an operation on the right-hand side and using the output to store in variable name 2. Here's a slightly more interesting example. I guess this pretty much recapitulates what I said before. So you've got a goal, which is the first target here, which is all. That's sort of the canonical normal target. And in this case, I've actually got two separate compilation units. So I'm saying that my program depends on these two object files. But again, to generate the object files, I'm just using sort of the standard formula for C. And I've just included that C flags is also sort of a standard thing to do. So this make file would depend on a lot of built-in knowledge, but the fact that you can define these extension rules however you want gives you a lot of power. So none of this is actually compiler specific. All of it is really dependent on files, their timestamps, and programs to transform files, with a little bit of magic that has to do with the extensions. You can actually generate dependencies automatically. This is kind of an interesting trick that some larger programs packages use. The C compiler has a special flag that will not compile the code, but rather just emit the dependencies that the C compiler understands. So in C, for instance, you have a .c file that has includes, #include declarations, and it will generate a line like this that just says, if I were to compile main.c, I notice that it refers to not just the source code, but it also includes main.h. And this is often used as an automatic way of avoiding skew between the make file and the sources. So, if you add another include in your sources, you don't necessarily have to update your make file, even though the make file has to understand the dependencies in your sources. So canonically, this is a make depend rule. You choose some string to hold your dependency, your generated dependencies, and then you actually include them in the make file, which is a pretty powerful thing because this include can also be conditionalized. It can also, you can run multiple includes, you can use subdirectories, all sorts of things like that. I've implied some of the structure of make, but it makes sense to keep these things in mind when thinking about how make works. So make has targets. Those are the things you want to generate. Usually you just have one thing that you want to generate, and then it has rules for deriving targets from things you have. It has variables, which are just ways of factoring out parameters, basically. Obviously, it has a make file, but there can be multiple make files. You can have make files in recursive in subdirectories, for instance, that are still made by make running in the root directory. And then I mentioned files. And the reason I mentioned that is because I wanted to circle back to this issue of the timestamp of files being important to how make thinks about satisfying dependencies. So if you want, you can just use symbolic names and have make do behaviors that don't depend on files. But the laziness of make derives from when your internal targets and dependencies correspond with files, and make can look at the timestamp of files to understand when dependencies are already satisfied. So in that canonical example, I had, the .o files are derived from .c files. So if a .o file exists and it's newer than the .c file, I know that dependency already is satisfied. And because make reads the make file, computes the dependency graph, and then tries to satisfy it, it can satisfy it by noting that there is an up-to-date derived file. So the targets, sometimes referred to as goals, it can just be the first rule in your make file. You can also specify it explicitly by saying this default goal is myprog. You can also specify it on the command line. So typing make all or make depends is pretty common. But like I said, the laziness really has to do with when depended on files exist with a timestamp that's newer than the dependencies. Rules come in two different formats. Make has been around for decades, so of course there's some buildup of, I guess you'd call it technical debt. The old format is more oriented towards the simple structure of .c files and .o files, simple compiler things with probably single letter extensions. The newer syntax is different in an interesting way. For one, it's flipped around. So this syntax is saying that a C file produces an O file, whereas this syntax is saying an O file depends on a C file. And so in general, avoid the old format just because this logic is probably more attractive. This percent character is also the wildcard here. So when you say %.o depends on %.c, implicit in that is that some substring matches. So an extension.o, when an extension.o is found, the stem or the matching part is treated like a variable. And so this is saying that foo.o depends on foo.c. And it's actually slightly more general than that. You can use both prefixes and suffixes. And there's nothing special about using the dot character here for extensions. So if you wanted to do something that wasn't more traditional and compiler oriented, you could use both prefixes and arbitrary suffixes with this format. The format can also express multiple dependencies on both the left and the right side. The most obvious way that works is in cases like where you have a .o file that depends on a .c file. It might also depend on a .h, a header file, for instance. The body of the rule, like I said, is interpreted by the shell. You can control which shell. That's pretty uncommon to use. The variables that you've defined in make are interpolated in the body before handing them to the shell. So this means that there's a syntax, well, depending on what you're doing in the body, because it's shell, you can use shell variables if you want, but it also means that you can pass make variables into the shell, as well as use shell variables. And the body is defined by the tab prefix. Variables, I mentioned eager and lazy evaluation. That's really important to understand. In some cases, it causes serious performance considerations. Another interesting thing about this is that I just showed wildcard here, but there are some other functions that you can run. This syntax is a bit like a modern shell invocation, but it's called wildcard. It really should be called glob, but wildcard is friendlier, I guess. This is just saying match star.c in the current directory, and all those results get treated as this variable. You can also transform extensions. So you can say, take a variable that consists of multiple file names, each of which is, let's say, .c, and transform all of those into .o. I should have written down the syntax here. I think it's something like $, star.c : star.o. I'd have to look that up, but it's a syntax similar to this that's basically just saying, you have variables and you're going to transform the extensions. You can also do interesting things like read the standard input from make into a variable, which is kind of a weird thing to do if you think of make as just being a build tool, but make is actually pretty general, and you can do things that are not build tools with it. So you could pipe things into make, for instance. I'll just mention that make files canonically is capitalized. You'll also see lowercase. Sometimes you also see GNU make or gmake file written out. As I mentioned before, you can split them up. You can include them together. You can include generated context. They can be recursive. Usually this means subdirectories. So that you can split up your program into multiple directories and you don't have to see a whole mess of files in one place. I think I've just got a couple examples to show here of really just to start off the conversation about weird things that you can do. So I mentioned that make is parallel. And there's not really that much to say about it, because if you run make with, like I say, -j2, it will satisfy the dependency graph 2 nodes at a time. So if you think of the dependency graph as potentially multiple nodes wide, you have many C files that you need to compile to .o files. This make -j2 will process them 2 at a time. So it'll run whatever rules you've defined 2 at a time in parallel. And of course, this can be different numbers. You can run, I think if you run with make-j, I'm not sure whether it's infinite or whether it tries to auto-detect the node. Generally, you should run make-j with a number here. Whether it's 2 or 32 is just up to you. But this example is sort of an interesting one because it gives you, it demonstrates that you have some additional control over the parallelism of your make. So in this make file, so this is not running compilers. These are not referring to files. These are just arbitrary strings. So the default goal is all, and I've said that it depends on 4 subsidiary goals, 1, 2, 3, and 4. And I've defined these subsidiary goals here. And this is a rule syntax, which is unusual, perhaps, but it's available as well if for some reason you want to do one-line rules. I think this would be absolutely equivalent to if you did this with a tab character. But this was the example that I wanted to show. So this is saying that these symbolic targets can be satisfied using this rule. And this rule just does, it just prints out the string that's being satisfied, the target, the singular target, and then does a sleep 5. And if we run this with make, nothing unusual will happen. It'll print out 1 because that's being substituted here, and echo. Oh, I should mention this @ sign at the beginning of a rule means don't show the command, just run it. So when make runs commands in the body of a rule, it will normally show you the command it's running in addition. And this is just a way of cleaning up the output a little bit. So when I say @echo and then some variable, the shell make will not show the shell command before it runs it. So if we run make here, we'll just see 1 printed out and then sleep 5, and then 2 printed out and then sleep 5, and so on. If we run make-j2, we get a different behavior because the dependency graph is 4 branches. Well, it's actually 3 branches, which are parallel, and then a join, and then 4 after that. So maybe I should have drawn this out. But the dependency graph for this has a 3-way branch, because these are unconstrained. But this .wait keyword means that all of the previous targets have to be satisfied before this target. And that's really important in general because in a complex program, even if you're using compilers and so on, you might have files that need to be generated before other files that you haven't necessarily encoded in dependencies. So another way of saying this, I could actually say that 4 is dependent. I could say something like 4 is dependent on 1, 2, 3. And that syntax would create a dependency in the graph as well. I think it would actually produce the same effect. But this .wait, and there's actually another syntax, .no parallel, which allows you to control parallelism. When I run -make j2, the first 2 of these will be run in parallel. Then the next one will be run potentially in parallel, but there's nothing to go in parallel with it. And then once those are done, then we can run 4. So this will actually wind up taking 1 and 2 in parallel, which takes 5 seconds, 3 in parallel, which takes another 5 seconds, and then 4, which takes 5 seconds. I'm only using 5 seconds to make it meaningful in what order it runs. Here's a funny example that has nothing to do with compilation, but illustrates a number of additional things. One is that I'm using shell syntax here. It's actually not shell syntax, it's Unix interpreter syntax. So an executable file under Unix is examined to determine what interpreter to use for it. And that's kind of a strange way of putting it to most people. But from the Unix perspective, if you try to execute a file, what you mean is you want to run that file through an interpreter of your choice. And so if you have a compiled file, it turns out the interpreter of choice is the Linux loader. So Linux loader understands ELF executables. It loads them, it maps them into memory, it jumps to the machine code, stuff like that. For shell scripts, you might have seen this bash bang, the hash sign exclamation point syntax. With shell scripts, the hash bang exclamation point syntax says the following string should interpret this file. And so this is an executable file that uses make to interpret it. And the rest of the body is make. So it's an executable make. You don't have to type make with this file name. You can just type the file name. In this case, I've just defined a list of hosts. I've defined a default target, which is all. So the default target is the thing that runs, the thing that is satisfied when this program runs. And it depends on these 3 dependencies. Each of these dependencies has a rule associated with it. And because I haven't used .wait or anything like that, if I run this in parallel, it will execute these lines in parallel. And these lines just print out the file name, and then they SSH to the host and run the uptime command. So, this is sort of fairly advanced shell syntax because it's using the backticks. It could actually be using, I think it could be using, actually, that's interesting. I don't know what happens when both make and shell use the same syntax. So you might be aware that backticks in shell are sort of equivalent to this syntax, but I don't know offhand what make does with this. I think it would probably choke because this doesn't really look like a make variable substitution. We can avoid that just by using the shell backticks, which means we're telling the shell, echo a string that includes interpolation of a command, the output from a command. This also illustrates a sort of an obscure make fact. Because in make we have these symbolic names, but we also are checking for the existence of files. Phony is basically saying that all is a symbolic name and not a file name. And without this line, if we had a file in the directory called all, and we tried to run this, it would just say all is up to date, because it would see a file that has a recent timestamp, and it would say all is our target. So we need this line to tell it that that I guess this is actually sort of I guess this is actually in some ways redundant. In most cases, if you use a symbolic target in make, you should probably have a declaration that those symbolic targets are phony, just to avoid scratching your head when you have a file of that target name. There are lots of other examples that you can find on the web. I found one, I'm not sure I have it at hand, that was using, I guess implicit in this is that these rules can be as complicated as you want. So for instance, the example I found on the web, which I didn't paste in here, it was using a very simple text processing scheme where it had a number of input files, let's say, different books. And it had a Python script to count the number of words in each book. And then it had a rule to sum across the number of books. And it was kind of a silly example, but what it was trying to demonstrate is that the rules are just operations on one file to generate another file. And then once that file is generated, that can be operated on by additional rules. So really, the field is quite open about the domains that you want to operate these things on. There's no assumption. For instance, here you're going to multiple machines. There's no assumption that all of the targets have to be files. There's no assumption that every transformation has to be compilation. You could do any sort of batch processing. So if you had hundreds of cases that you wanted to run through a program, let's say GrowMax, there's no reason that you couldn't list the cases. There's no reason you couldn't use syntax. Forget what I have it here. There's no reason you couldn't use syntax to auto-generate. So for instance, you can say sources star.c. You can generate variables that represent pattern matches. I guess the best example I had was that wildcard pattern. Yeah, so this would be useful if you had a whole bunch of cases, let's say suppose you wanted to run a whole bunch of Gaussian. So Gaussian input files typically have a .gau or similar extension. So you could use this to expand a variable. You could say cases like this. And then you could have a rule to generate, you could have a rule that says, I want to take a .gau file, and I want to generate a I forget what the output is, log, something like that. And to do that, I run Gaussian dollars at into the dependency. So it should be something like this. And establishing a rule like this allows you to run an arbitrary program. And this would run you could use this to automate parallel Gaussian across any number of cases. So I guess all I'm saying is that there's a big toolbox of things that you can use potentially to do non-traditional things with make. And my intent is just to open the floor now to questions and potentially discussion of these features.